Hi, good evening, everyone. In today's lecture, we are going to talk about the performance metrics and measurement of the computers. So, in this week, we are going to cover the topics like the performance metrics and the measurement of a computer and the CPU performance equation, Amdahl's law, and the benchmarks which are evaluating certain applications and application suites. So, and then we try to cover some of the simulators which are used in the for executing these computer architecture programs. So, for these topics, we can go through the computer organization and the design textbook. Some optional readings we can go with this text, which is from the chapter 4, which is having this assess the assessing and the understanding performance and computer architecture. The second textbook from where we follow some of the topics from chapter 1.8, which is the measuring, reporting, and summarizing the performance. So, in performance metrics and measurement, and we say that when we try to do the computer performance assessment, and when we talk about the computer performance, we need to consider a few things. The first one which we cover is method of performance equation. First one is the method of your performance equations, or we say this evaluation. So, what is this method of performance evaluation? That means in this issue, you can see by what measures will the performance be assessed, or will the assessment be local to a specific part of the computer hardware or global. So that is across all hardware and software modules, or what will the mix of your instructions be? So that comes the first issue when we talk about the computer performance, that is method of performance evaluation. And second issue comes that the limitations of evaluation, the limitations of your evaluation. So what it means, what are the shortcomings of each method or measure of performance assessment, and from when do these limitations arise and why, and what are or what can be done to improve these limitations. So that comes into the second issue of your computer performance when we talk about computer performance. Similarly, the third issue is what are the metrics? What are the metrics? That means what the formal measures are to be used for performance evaluation. It may be speed, it is speed or time used in a computation or memory space required. So what measures do we use? Your speed or your or the memory space which is required, or any computational or time which is used for your computation, or in terms of we say that the time. So what metrics that we use for the computer the performance evaluation? And the fourth one is say the another issue is processor performance equation. Processor performance equations. Processor performance equations means what? How will the processor's performance be described mathematically? Does the equation portray the actual parameters of practical interest, or does the computational model described by the equation not match the processing architecture under test? So these few things comes under your processor performance equation. And then the another issue which comes that your or we consider that your AMDA the performance evaluation reports, the performance, the evaluation report, performance evaluation reports means what methods of analysis and presentations are used to evaluate data. Is the data normalized to a particular benchmark result or parameter? Is the normalization performed in a physically meaningful way? So these kind of things will be present in your the performance evaluation report. And the sixth case is your the Amdahl's law. We say the Amdahl's law. So here, whatever the measurements are made, as one continues to enhance processor performance, the overall improvement achieves diminishing the returns. So we examine each of these issues. Maybe method of performance evaluation and the limitations of your evaluation, what kind of metrics we use, whether we use speed or memory space requirement or time, or your processor performance equation, or performance evaluation reports, and the Amdahl's law. So we'll see this. So why these schemes means, as we said, these issues, when we talk about computer performance, we should consider all these issues to assess the performance of your computer. So let us see. So what is the performance metrics means to come to this one? When we say one computer has better performance than another, that means what is? So if we have two computers, suppose if I have two desktops, and if I have a program, suppose single program is there, if this program is given as an input to this computer 1 and computer 2, then what we see, what do you mean by which computer is performing better than another means, if these computers are suppose your desktops, these computers are suppose the desktops, then we would say that when we running a program on computer 1 and computer 2 and they are the desktops, then we would say that the faster one is the desktop computer that gets the job done in first. Means what? Suppose to execute this program, suppose this computer 1 takes suppose the 5 seconds of time, for example, and computer 2 takes suppose 10 seconds of time to execute the same program, then what we can say, computer 1 is performing better than computer 2. Computer 1 is performing better than computer 2. Suppose in other case, if these computers are, if you are running the data center, in that data center instead of desktops we use the servers. We use the servers, right? If these computers are, this is server 1 and this is suppose server 2, then what it will be done, the servers, the several servers running the jobs submitted by many users in that data center, then we would say that the faster server, the computer means here is the server, the faster server was the one that complete the most jobs during the computer, most jobs during their execution. So we call this as your throughput. So for performance evaluation, of any the computers, or the computer performance evaluation is primarily based on your response time, and your your throughput response time and throughput. So the throughput is how many bits of data are processed or how many operations are performed in a given interval of time. Whereas, for example, we say that a processor has a throughput of, suppose, the n MB per second, n MB per second, or we say the megabytes per second. Then with respect to the execution time of this program on a processor, suppose X, for a processor X, we can say that the performance of X is the reciprocal of its execution time. So that we as we said that the performance metric is based on the throughput and the response time. Okay, so throughput means if you are using the desktops, we talk about the throughputs. If you are using, when you are using the servers, we talk about the throughput. When you are using the desktops, then we talk about the response time. So what is this response time? The time between the start and completion of a task. So this task may be, in our case, we consider of any program. Okay, the response time is the start and completion of a task, and it is also referred, sometimes this response time is also referred as your execution time. So what is this execution time? The total time which is required for the computers to complete a task, that includes you are including the disk access, memory access, input output activities, operating system overhead. So if you recall our example when we talked about the implementation of your instructions, said what we did, we have the memory, we have the main memory. In the main memory, the instructions are stored in the form of your zeros and ones, and when these instructions are supposed to be executed by your CPU, central processing unit, then first it is the disk is accessing, means the memory is accessed to read this information, the instruction from the memory, and store into your instruction register. Okay, so that this execution time, this reading, writing, and executing, that includes, to complete this task, that includes all these. But we are interested only in the CPU execution time. So within the CPU, within the central processing unit, we have this ALU unit, we have the control unit, and we have some register file. So that consists of your all registers, and we have the instruction register and your program counter. Okay, so within this CPU, how these instruction registers are decoded and gives that signals to your ALU, and once decoded, how the data is going to store in the registers like R1 and R2 and R3, like so that time, total time, we take it as your the execution time. Execution time. Okay. So as said, the response time, we talk about the execution time of your processor. Execution time of your processor. Whereas your data centers of often interested in increasing the throughput, means how many jobs or how many tasks are completed in a given time. That means what? If I have a server, if I have a server, for that server, the only the 5 minutes time is given. 5 minutes time is given, and for the this server can be accessed by many users. This servers can be accessed by many users. User one, your user two, your user three, and user four. Suppose in this example, these users can give the task, the task. So T1 task given by user 1, T2 task given by user 2, T3 task given by user 3, and so for the single server, and given the time is in 5 minutes time. In 5 minutes time, if this server, how many tasks it is executed, if it completes all four, then we say that the throughput of this server is 100%. 100%. But in 5 minutes, if it completes only, suppose, the two tasks, then the throughput of this server, we called it as your, 50%. 50%. Okay. So in performance metric, we mainly focused on the response time, means your CPU execution time, and the throughput. And the throughput. So as we said, when we consider this response time, we maximize the performance. We maximize the performance, as we said. If we want to maximize the response time or the execution time for some task, thus we can relate the performance and execution time for any computer X. So the performance of X can be described as the performance of your computer is reciprocal to its execution time. Reciprocal to its execution time. Okay. So if the execution time is less, then its performance is increased. If performance is decreased, means execution time is more. So it is in reciprocal. So when we comparing the performance of suppose two computers, computer X and your computer Y, and if the performance of X is greater than the performance of your Y, suppose the performance of your X is greater than the performance of your Y, then that can be written as performance of X is greater than performance of Y. Performance of your Y. So then these performances are in reciprocal to their execution time. So the performance of X can be written as 1 divided by, so because this performance is equal to, it's a reciprocal of your execution time. So performance of X is derived as 1 divided by execution time of your X, and performance of your Y is the execution time in terms of execution time is 1 divided by execution time of Y. So when you simplify this, you will get the execution time of your Y is greater than the execution time of your X. That means what? The performance of X is greater than the performance of Y, means the execution time of your X is less than the execution time of your Y. The execution time of your Y. Okay. So from there, if the processor X is faster than your processor Y, as said, then the execution time of X is less than your execution time of Y. So the relative performance should be less than 1. The relative performance. And when this is happening, then the relative performance should be less than 1. The relative performance should be less than 1. And this also implies that increased throughput of your X with respect to your Y. Increased throughput of your X with respect to y. So here that we can write this, the comparing this design alternatives, we can write this, the execution time of your y is n times execution time of your x. As said, so performance of your x is faster than your y means x is n times faster than your y, n times faster than your y, or we can say this as well relative performance. So as a result, we want to improve the performance by increasing the performance, which means decreasing execution time. So in practice, this can be done by decreasing response time or adding more processors to a system which provided input output is managed efficient, right? So that you can give this relative time, you find that execution time of your y divided by your execution time of x. So that in terms of its performance means your performance of your x divided by your performance of your y gives the relative performance of your x and y. So these equations are very important. These equations are very important for for your assignment as well as for your examination purpose also. Would you please comment on midterm 2? Yeah. At the end of the class, we'll discuss about those. So then let us take this relative performance example here. We just consider. So for example, if a computer X runs a program 10 seconds and computer Y runs the same program in 15 seconds. So how much faster is X than Y? That means you can find a relative performance of your X and Y. So we know that X is n times as fast as your Y. So if performance time of your X divided by your performance time of your Y, that is in terms of its execution, the execution time of your Y divided by your execution time of your X, that gives the relative performance. So thus the performance ratio here is the execution time of your Y is 15. The execution time of your Y is 15 and the execution time of your X is 10. So that gives 1.5, the relative performance. That means we can say that X is therefore 1.5 times as fast as Y. Or we can say Y is therefore 1.5 times as slow as X. So let us see, we could also say that computer Y is this time slower than your X as said. So since the performance of your X compared to your performance of your Y is 1.5, means that the performance of your X is 1.5 times of your performance of your Y. Right? So see, for another example, suppose there are two programs, program 1 and program 2 in terms of seconds. So here computer 1 executes program 1 in 1 second, executes program 2 in suppose 1000 seconds. Then to execute these two programs by your computer A, it takes 1001 seconds. Similarly, the same programs which are given as an input to your computer B, then if it takes to execute program 1, it takes 10 seconds, and to execute program 2, it takes 100 seconds. Then the overall time taken to execute these programs by your computer B is 101. So how to compare the performance? That means the total execution time. The total execution time by both the computers. So a consistent summary measure, the consistent summary measure, comes from this. From this example is the performance of your B divided by your performance of your A is equal to execution time of your A divided by your execution time of B. So the execution time of A is 1001 and execution time of B is your 110. So what it means, the execution time of A is 9.1 times, taking time to your execution time of your B. The relative performance of your X, A and B. So as we are saying that for measuring the performance and the performance metric, the time is the measure of your computer performance. Or we can say that a program that is executing or has been executed has the following, some of the components you can see here. What are those? One is wall clock time or CPU time or input output time or other times like response time or your elapsed time. So what is these times? And these times, the wall clock time or response time or elapsed time, which is the latency to complete a task. So complete a task means which includes the disk access, memory access, input output activities, the operating system overheads and everything, but we are interested only in your CPU time, CPU execution time, CPU execution time, right? So that is the processor's performance equation. We need to find out. So here the CPU performance equation, which is essentially all computers are constructed using the clock runnings at a constant rate. Clock runnings at a constant rate. So this discrete time events are called your ticks, or they can call as your what you call the clock ticks or clock periods or clocks, or cycles or clock cycles, or computer designers refer to the time of your clock period by its duration, that is 1 nanosecond, or by its rate 1 gigahertz. So here, when you talk about this CPU performance or measuring the performance, as we said, it can take the measuring this performance, it takes wall clock or response time, right? So what is wall clock time? How long it takes for your program to execute from the time it is invoked to the time it completes. So this time is measured with respect to a global time standard. So we name it according to a common object such as your wall clock. So this is also called the elapsed time. Yes, this is also called your elapsed time. So then we are talking about your CPU time. So CPU time comprised of your user CPU time and the system CPU time, and the system CPU time. So system CPU time means the time the operating system spends supporting the program. So we measure a program execution time using the Unix time command. If you are using the Unix operating system, you can simply write the uh, Unix time command in the terminal. So then you can find how much time that the processor is taking to execute a directory. Okay. So there, if you execute that one, you will find the four numbers will be there in that, this clock time. That suppose, for example, when I try to execute the command, like Unix command time du for any data unit command time in the CPU, I got the response at 0.21U and 1.54S and 0 of 24.49 and 7.1 percent. So when you execute this command for a directory, for at one root directory, then you get this response. So these four numbers have the following manners. So this is having four numbers, the following manner. So what are those? Here it is very clear that it is U 0.21 U, that is the time taken, or the CPU time, that is 0.21 seconds, the first number which is spent by the users. So user CPU time. The second one is S. This is the system CPU time, that is 1.54 seconds. That is the second number in this case. And third one is your elapsed time. Your elapsed time is given 24.49 seconds. And finally, the CPU activity as the percent of your elapsed time, 7.1%. 7.1%. Right? So the observe that the percent CPU activity is computed as in the first step. Add the user and system CPU time to get the total CPU time. If you add this user and system CPU time, you will get the total the CPU time. So what is the total CPU time that you will get by adding this to the user and system CPU time? You will get 1.75 seconds, right? And second one is divide the total CPU time by elapsed time. Divide this total CPU time by the elapsed time. So our elapsed time here is 24.49. 24.49. When you divide this elapsed time of your total CPU time, divided by your elapsed time, then you will get the total CPU time by your elapsed time. Then you will get the percentage. So next, in step 3, you multiply it with your 100. That will gives to the total percentage, or we can say that the percentage of your system. So given a method of measuring time and the computation of different times, from these measures of time, we can now discuss a simple model of computation for measuring the CPU performance, that we call the CPU performance equations. CPU performance equation. So to do this CPU performance equation, in order to measure the CPU performance in a physical, realistic way, we need a model of computation. In the simplest way, or in the simplest case, we say we start with the number of CPU cycles defined the number of CPU cycles defined for program. So the CPU performance equation, you can write the CPU execution time for a program. CPU execution time for a program. So if you take a program, I have a program, I can write this program as the one program which I am having, suppose uh, load R1, R2, then store your R2, R3, then subtract your R1 minus R2, and then you can move. This is just an example of move R3, R4. So I have one program. That program is having these instructions. I have a program. That program is having instructions. How many instructions? I'm having 4 instructions in that program. So to execute this program, the execution time of this program, okay, or the CPU time for program can then be expressed in 2 ways. In what way? The CPU execution time for this program is calculated as the CPU clock cycles. CPU clock cycles for a program. So how many clock cycles are required to execute this entire program, which is multiplied by clock cycle time. Clock cycle time. Or alternatively, that because this clock rate and the clock cycle time are the inverse, so clock cycle time can be written as 1 divided by your clock rate. Your clock rate. Okay, so you can write this as the CPU execution time for a program is calculated as or evaluated as your CPU clock cycles, number of clock cycles for program divided by your clock rate. Okay, or you can say this as the number of clock cycles or number of cycles is equal to, as we said, the CPU cycles that defined as number of CPU cycles, number of your CPU cycles is equal to how many instructions are there in that CPU, and that is multiplied by the CPU cycles per instruction. And this can also be defined, for example, if a program runs in 10 seconds, on computer A, which has 2 edges in clock, and a computer designer trying to build a computer B. So which will run this program, the same program in 6 seconds. So the designer has determined that the substantial increase in the clock rate is possible, but this increase will affect the rest of CPU design, causing computer B to require 1.2 times as many clock cycles as computer A for this program. So what clock rate should we tell the designer to target in this example? So we need to first find the number of clock cycles required for the program on A machine. So the CPU execution time or the CPU time for a program on machine A is given as your clock cycles per program divided by your clock rate. The CPU time per program is equal to the clock cycles per program divided by your clock rate. So your CPU time of your A is number of clocks required, cycles required for a program on A, and its clock rate. So from here it is given a program runs 10 seconds, runs in 10 seconds on A. Okay, and which has the 2 edges of your clock. So that means what? The execution time of your A is 10 seconds. So this execution time is 10 seconds. So 10 seconds is equal to clock cycles divided by the, here it is given 2 edges. The clock rate is your 2 edges. So this 2 edges will be written as 2 into 10 to the power of 9, 2 into 10 to the power of 9, that is cycles per second. So when you simplify this, then this clock cycle is equal to, when you take this to this form, then 10 seconds multiplied with 2 to the power of 9, 2 to the power, 2 into 10 to the power of 9, number of cycles divided by seconds. So this second and this second will get cancelled. So we'll get 20 into 10 to the power of 9. 20 into 10 to the power of 9 cycles. So for clock A, how many cycles are required? Means 20 into 2 to the power 10 to the power of 9 cycles are required for computer A. So then how many clock rates should be there, required for your designing 2 means comparison will take place. So CPU time for B can be found by using this equation. CPU time of B is, from here you can say this, your the CPU the computer B is to require 1.2 times as many clock cycles as computer A. 1.2 times as many clock cycles of your computer A. So that is, your CPU time of your B is equal to clock cycles of your B. So clock cycles of your B, your clock cycle of your B is given that 1.2 times of your clock cycle of your A for designing, divided by your clock rate of your B. So here CPU time which is taken, example is 6 seconds. 6 seconds to execute the same program. So 6 seconds is equal to 1.2 into clock cycles of your A. So clock cycles we found in the here is, the clock cycles which you found here is 20 into 10 to the power of 9. 10 to the power of 9. So that you can add here 1.2 times 20 into 10 to the power of 9 cycles of your A divided by your clock rate of B, because we are interested to find in B. So clock rate of B is equal to the 1.2 into 20 into 10 to the power of 9 cycles divided by, this comes this side and this goes here. So it becomes the 0.61s are 6, 0.2s are 12. So we'll get 0.2 into 20 into 10 to the power of 9 cycles, which is equal to your 4 into 10 to the power of 9 cycles. So 2 2s are 4, it will become 40. So your decimal is there, so you will get 4 into 10 to the power of 9 cycles. So total 4 gigahertz. Total it will get the 4 gigahertz. So note that to run the program in 6 seconds, by your computer B, it must have twice the clock rate of your A. Twice the clock rate of your A. Right? So then how to improve the performance? How to improve the performance of your computer? So this can be given the equation that the CPU execution time is equal to, we said, many seconds are taken for program. Seconds per program. Seconds per program, that gives your execution time, right? So seconds per program means it is given. Seconds means how many cycles per program. Cycles per program, that means for how many cycles, how many seconds per cycle. How many cycles per cycle. So to improve performance, everything else being equal, but you can either increase or decrease. You can either increase or decrease the number of required cycles for a program, or the clock cycle time, which is said to another way, or the clock rate. That means what? To improve the performance, you will consider how many number of cycles required for a program. Number of cycles required for a program, or the clock cycle time in terms of seconds, or the clock rate. So the answer for this you will get: to improve the performance, you can either decrease the number of required cycles per program, number of required cycles per program, or you can decrease the clock cycle time, or you can increase the clock rate. You can increase the clock rate. Okay. So, from this equation, you can find again. To improve this execution time, that means what? Either you can, this is the execution time increasing, means your clock rate is decreasing, right? In our example, we have seen when clock rate is increased from 2 gigahertz to your 4 gigahertz, for A it takes 10 seconds in our previous example. For B it takes 6 seconds. So see, to improve the performance of your execution, either you can increase the clock rate, or you can decrease this number of cycles for your number of cycles, or you can decrease the execution time, that is not given. The number of cycles required for program, that should be decreased, or you can decrease the clock time, or you can increase the clock rate. So then comes to the instruction performance equation. Instruction performance equation. So in this instruction performance equation, you can see, to execute the instruction of a program, as we just consider, like, we are having instruction 1, your instruction 2, your instruction 3, your instruction 4, and so and so. Then in this instruction performance equation, how many cycles are required for a program? How many cycles are required for a program is important for this instruction performance. So could we assume that the number of cycles equals to the number of instructions? That means every instruction takes the same time. So for that, you can see that for first instruction, it takes, suppose, 1 cycle. For second instruction, it takes one cycle, and so and so. So assuming that is that number of cycles which are equal to the number of instructions, that means this assumption is incorrect. Different instructions take different amount of time on different machines. So if you recall the example of your the register instructions and your memory instruction. Suppose for register instruction, the operation like R1 is equal to your R2 plus your R3. Then what you did, you simply provided the operands of your R2 and R3 addition operation performed and given to it. But when you talk about the memory instruction, R1 is equal to R1 is equal to your R2 plus your R3 in square bracket. So what it means here, this is the memory means first, before executing this instruction completely, it first go and calculate the value of R3, where R3 is having the address of an operand. So first this operation is executed, then the result will gives here, then this operation. So this may complete in one cycle, this instruction may complete in two cycles. Another one is, if these two instructions are executed on two different machines like A machine and B machine, for A machine, it may take only 1 plus 2, 3 cycles, clock cycles. For B, if it is slower one, it may take 4 cycles, 4 clock cycles. So that's the reason for instruction performance, how many cycles are required for a program means, it is, we cannot say that we assume that number of cycles is equal to number of instructions, means that become incorrect. Reason is different instructions take different amounts of time on a different machine. So different number of cycles for different instructions. As we just saw, some instructions may take 1 cycle, some instructions may take 2 cycles, remaining may take 1 cycle, some may take 3 cycles, different. So example is, multiplication takes more time than your addition. And if you are having the floating point operations, that takes longer time than integer ones, as we saw in the previous example. For floating point, to represent the IEEE 754 format, what we did, first we converted the decimal number into the binary. Then in the second step, this binary number is normalized. Okay. Then in the third step, we calculated the exponential. Then in the fourth step, we represented this floating point, number. But whereas in integer simply the decimal number is converted into binary. So the number of cycles required for integer one is less than the number of cycles required for your floating point. Similarly, accessing memory takes more time than accessing register. I just saw the example, R1 is equal to R2 plus R3 takes 1 cycle suppose, and if R1 is equal to R2 plus your memory instruction, R3 takes more time, because here we are accessing the memory. So here the important point is, changing the clock time often changes the number of cycles required for various instructions. So for example, the instruction performance, the components of your performance is, as we said, the CPU execution time for a program that use the units or measures in terms of seconds for a program. But whereas in terms of instruction count, how many instructions executed for the program, whether all the instructions are executed or some instructions are executed. And in advance to that one, the clock cycles per instruction, for executing every instruction, how much clock cycles are required. So we write it as your clock cycles per instruction. So then for clock cycles per instruction, what is the clock time? So this clock cycles per instruction means average number of clock cycles per instruction. And your clock cycles means the seconds per the clock. So by using these metrics or the measuring unit, you can write this: the CPU clock cycle is equal to, the CPU clock cycle is calculated is equal to number of instructions per program. If program is having suppose 5 instructions, then 5 instructions. For every 5 instructions, what is the average clock time it is taking? That is the average clock cycles per instruction. So then the CPU clock cycle can be written as your CPU time, the CPU execution time is equal to instruction count, number of instructions in that program, which is multiplied with your clock cycles per instruction. Suppose 5 there means five instructions are there, means first instruction may take 1 cycle, second may take 3 cycles, second instruction may take 3 cycles, plus third instruction may take 4 cycles, and fourth instruction may take 1 cycle, plus your fifth instruction may take 1 instruction. Then it gives the average total 5 instructions. So that is average time. And then the clock cycle time. So this instruction performance equation is simplified as the CPU clock cycle is equal to your instructions per program, which is multiplied with the average clock cycles per instruction. And that is simply written here as your CPU time is equal to instruction count, your CPU cycles per instruction, the clock time. So the performance of a processor is determined by the instruction count of a program, that is the compiler and the instruction set architecture determines this instruction count, and then the CPI, that is the cycles per instruction. Okay, so you can see I have a program. So the execution for this program by your CPU, suppose your CPU is equal to, in that program, how many instructions I'm having? Instructions. Okay. Okay. This program is having the number of instructions. Like one is your register instruction. You can write R1 is equal to your R2 plus your R3, and another one is R2 is equal to suppose R4 is equal to R5 plus your memory of your R6, or you can write R7 is equal to your R1 plus 5, your R8 is equal to you may write this R1 plus your R2 in this storage, or to memory location will be there. So it may take 1 cycle. As I said, instruction count, the CPU execution time is for this program, how many instructions are there? 1, 2, 3, 4 instructions. So 4 instructions. For every instruction, how much? The clocks per instruction, the clock cycles per instruction. For this, suppose 1 clock cycle is taken. For this, it requires 2 clock cycles. For this, it is immediate, so it requires the 0.5 clock cycles, suppose, and it requires, suppose, 4 clock cycles. So it gives clock cycles per instruction. Then clock cycle time. So how much in terms of your seconds. So this clock cycle time means the rate, that is to implementation of the processor determines the clock cycle time. So consider this example to better understand. Suppose we have 2 implementations of the same instruction set architecture. Okay. So that is, computer A has a clock cycle time of 250 per second and a CPI of 2.0 for some program, and computer B has a clock cycle time of 500 PS and CPI is 1.2 for the same program. Then which computer is faster for this program? Which computer is faster for this program and by how much? So then we can say that each computer executes the same number of instructions for the program because they are having the same programming, same number of instructions. So number of instructions are same. Second, from this one, the second one is, let's call this number of instructions like I, the number of instruction. So first we find the number of processor clock cycles. Processor clock cycles for each computer. So for each computer, clock cycles are given as number of instructions multiplied by the CPI. That is what we call, right? That the CPU time is equal to the instruction count multiplied with your CPI, cycles per instruction. So instruction count is multiplied with your the CPI. Similarly for B, it is multiplied instruction count multiplied with 1.2. So we assume the number of instructions are same, for in that program for both the computers. Then you can see compute the CPU time there. To calculate the CPU time, you require the CPU clock cycles multiplied with clock time. So for A, the CPU clock cycles which we computed is your I into 2, and multiply the clock cycle times which is required. Okay, so that is your 250 PS. So totally will have the 500 multiplied with your the number of instruction counts per second. Similarly, likewise, means this instruction may be any number of your program. So likewise for B, the CPU time of your B multiplied with its clock cycle, CPU clock cycle of your B multiplied with your the time which is taken by your CPU, that is 500 here, the clock cycle time. So it gives 600, which is multiplied with number of instructions. So 600 clock cycle time multiplied with number of instructions, and 500 clock cycle time multiplied with your number of instructions. That gives the execution time of A and execution time of your B. So clearly, computer A is faster compared to this. Computer A requires 500 seconds clock cycle time compared to your clock cycle, the CPU B. So the amount, the computer A is faster. So the amount faster is given by the ratio of its execution time. We know that. So the performance of A, to find the relative performance, because comparing two, so performance of A divided by performance of B is equal to execution time of your B divided by execution time of your A. So when you do this operation, it gives the relative performance of your A, which is faster than your B, means A is 1.2 times faster than your B. So we can write it as, and we can conclude that computer A is 1.2 times fast as computer B for this program. So then comes to the classic CPU performance equation, which we just discussed. So we can now write this basic performance equations for your instruction count, like the CPU time is equal to instruction count multiplied with the number of clock cycles required per instruction and the clock time. So instruction count means number of instructions per program. CPI means number of clock cycles per instruction, and clock cycle time means number of seconds required for one clock cycle. Or since the clock rate is the inverse of your clock cycle time, so we can write this. We can write this as your instruction multiplied with your number of cycles per clock, and this clock time will be written. This is equal to 1 divided by the right clock rate, or the clock cycle rate. So this is the summarized equation of the performance of your instruction, CPU performance of your instruction. And sometimes it is useful in designing the processor to calculate the number of total processor's clock cycles are required. So this is the CPU clock cycle is evaluated as the number of instructions in that CPU multiplied with your clock per CPU of your I processor. So where it is simply written as your IC means the number of times instruction I is executed in a program, and the CPI means the average number of clocks per instruction for the instruction I. So this is can be written as your, if you have the, when you are having the loop, suppose for loop, in that loop the same instruction may be executed n times, as we write I is equal to 0 to your I greater than suppose 10, and you write I plus plus. In that case, same instruction is executed. Suppose you write R1 is equal to your R2 plus R3. So this instruction will be executed in times. So every time its clock cycle per unit will be calculated. So this is, we call the average time or performance of the average time of an instruction. So consider the example here. For a compiler, designer is trying to decide between two code sequences for a particular computer. The hardware designers have supplied the following facts. That is, the cycles per instruction is given that for a computer A, the cycles per instruction requires only one cycle. For B, 2 cycles. And for C, 3 cycles per instruction is required. That means what? Simply, for A, it requires only 1 cycle per instruction class for computer A. For computer B, 2 cycles means what? Suppose if I have the instruction like R1 is equal to R2 plus your R3, computer A takes only 1 cycle. Computer B takes 2 cycles to execute this one. Computer C takes 3 cycles to execute this one. So for a particular high-level language statement, the compiler writer is considering 2 code sequences that requires the following instruction count. So we know this CPI is there, so we need to find out the instruction count. The instruction count is given that for programs, the code sequences, code 1 and code 2. For A, for code 1 sequence, it requires the CPIs for each instruction class is 2, and for second code, it requires 4 cycles. For B, it takes only one cycle. For C, it takes, for first code, it is taking 2 cycles. Second code, it is taking 1 cycle. So which code sequence executes the most instructions? Which code sequence, whether 1 or 2? Or which will be the faster one? Which computer will be the faster one? Is it A, B, or C? Or what is the CPI for each sequence? So to answer these questions, you can see this example. Our first question is, we are finding that which code sequence executes the most instruction? Code sequence executes the most instruction. That means the answer is sequence 1 executes 2 plus 1 plus 2, total 5 instructions. Whereas sequence 2 executes by these 3 different machines, like 4 plus 1 plus 1, 6. So therefore sequence 1 executes fewer equations. That means your sequence 1, code sequence 1 is having less instructions than your code 2. So this program 1 is having, program 1 is having only 5 instructions, like P1, consider this P1 and P2. So P1 is having only 5 instructions, like it may be like R1 plus your R2 plus, is equal to R2 plus R3. Another instruction is, suppose R4 is equal to your R5 plus your memory address R6. Or it may use another instruction that R7 is equal to your R1 plus 5. Or R8 is equal to memory address of your R1 plus your R6. So 1, 2, 3, 4, R9 is equal to 1, suppose. So this P1 is having 5 instructions in this code. So for P2, if you take P2, it may add suppose other instructions, 6 instructions. So these instructions are taking that the number of cycles for this instruction for each class taken by this one is the number of instructions in each code is this one. Code 1 is having 5, code 2 is having 6. So when you know this number of codes, which will be faster? Which will be faster means which computer will be faster to execute these instructions. Okay. P1 is having 5 instructions, P2 is having 6 instructions. So here the instruction count is 5, here the instruction count is 6. And here given that A is taking to execute any program, A takes 1 clock cycle, B takes 2 clock cycles per instruction, and C takes 3 clock cycles per instruction. So now calculate the which will be the faster, whether it is A, B or C. So the answer is we can use the equation for your CPU clock cycles based on instruction count and your CPI to find the total number of clock cycles for each sequence. So the CPU clock cycle for sequence 1, CPU clock cycle for sequence 2, which is calculated as the number of instructions multiplied with the instructions per cycle. So that is given as the CPU clock cycle for sequence 1, code 1 is given as it is multiplied with count 1, instruction count 1, okay, which takes 2 cycles per instruction 1. Second one is 1, okay. For A, it takes 2 cycles. For it takes 1 cycle, that is B multiplied with your 2, and your C multiplied with 2 for sequence 1. Okay, so that is number of instructions multiplied with the clock cycle. It gives total 10 seconds. Similarly for 2, so for code 2, okay, A requires 1 clock cycle. So for number of instructions, 4 is multiplied with 1. Similarly, 1 multiplied with 2, then 1 multiplied with 3, so it gives 9 cycles. So the code sequence 2 is faster even though it executes 1 extra instruction, because it is taking number of cycles less. Number of instructions are more in clock 2 or in sequence 2, but it takes less cycles. Whereas in clock cycle 1, it takes number of instructions are less, but it takes the higher cycles. Then last one is what is the CPI for each sequence? The cycles per instruction for each sequence. So then since code sequence 2 takes fewer overall the clock cycles but has more instructions, so it must have a lower CPU. So the CPU values can be computed as CPI is given as CPU clock cycles divided by instruction count. So CPI for code 1 is equal to number of clock cycles taken for code 1 is 10 seconds divided by number of instructions count is 5. So that is 2. And for CPU2, it takes 9 clock cycles for execute instruction 6. So it is 1.6 rate. So this is what is the CPI for each one means for each sequence. For code 1, it takes 2 seconds. For code 2, it takes 1.5 seconds. Right? So with this, I would like to stop this session.